Hello everybody, my name's Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation is about ice and rain protection. My usual disclaimer, please always treat your company training and their manuals as the authoritative source of information for your fleet. So, contents of this presentation, we'll be looking at the panels on the various generations of 737, window heat, thermal anti-icing, ice detection, icing, non-environmental icing, windscreen wipers and rain repellent. Okay, back in the beginning on the original series, the 1 and 200s, there were several significant differences from later generations. The first one was that, surprisingly, although the originals had an alpha vane, it wasn't heated. There's no left alpha vane caption on the pitot static panel. The wing anti-ice had a ground test position, as you can see down there, so it's a 3-position switch. And I'll come on to the logic of that on a later slide, because this was also used on classics as well. The engine anti-ice captions were quite significantly different. So cal valve open, this one was actually the same as later generations. It shows that the engine nose cowl leading edge is being anti-iced by 13-stage bleed air, tempered with ambient air. So that's a slight difference, because bleed air on its own would be too hot, so they actually mixed it with ambient air. But note that there was no amber cowl anti-ice caption, so just the blue cal valve open. The difference captions were these left and right valve opens in blue. They show that the engine inlet nose dome, so the spinner was heated. Also the compressor inlet case and inlet guide vanes. They were all anti-iced by 8-stage bleed air, and all of this was unique to originals. I think there's a school of thought which would say that having the spinner de-ice was quite useful. I've certainly encountered some quite strong icing on the spinner. But of course, those of you that will have seen my PowerPoint presentation will have seen the development of the spinner from conical to elliptical to conliptical to try and eliminate the need for anti-icing there. Anyway, I digress. So with the classics, there was the following changes: the left and right alpha vanes, because there were 2 on classics and later generations. They had heated probes and enunciated, as you see there. Only 1 temperature probe. Oddly enough, many of the originals had 2, but at least it was heated. The TAT test button made an appearance with the classics. Now this is only fitted on aircraft with an aspirated temperature probe, so you can tell by looking at this panel whether your temperature probe is aspirated or not. So the probe was unheated on the ground to prolong the life of the element. So you wouldn't quite know whether it was heated or not by switching the pitot statics on. So that's why you've got the TAT test button. If you press this, it simulates an airborne condition and allows the probe to heat up. So if you press that and an amber light illuminates, then you've got a fault on it. If you've got the pitot statics off, you won't see any change because they'll all be extinguished. If you've got the pitot statics on, pressing this will illuminate eliminate that light. So it's just testing an airborne condition. On the NGs, there's an optional either green on or amber off lights with the window heat. The photo here is actually of the green on. With the amber off lights, this is just fitting in with the dark cockpit concept, so you won't have the 4 green lights blazing into your eyes on a night flight. What you will see with the window heat on and functioning normally is nothing, which is great. If there's a fault with the window heat, then you will get an amber off light. The panel's called a subtle difference here. It's actually called probe heat, and on the originals and classics, it was called pitot-static heat. The the reason they needed to change it was because the static ports are not actually heated anymore, so they can't really call it pitot-static heat. I've highlighted the difference there that you can see with well, in this example, Captain's pitot. So the statics are now no longer heated. Is the takeaway point from there. Auxiliary pitot is now is now a thing and is added and is heated. From 2010, the probe heat switches were changed from the old on-off to auto and on. The auto position automatically applies probe heat whenever the engines are running. This modification was apparently made in response to reports that these switches were being occasionally forgotten by crew with the associated bad consequences. These probe heat switches can just be left in the auto position all the time, so there's no off position anymore. Or if your SOP requires it, you can move them to the on position. Either way, you will get probe heat automatically in flight, which is a good thing. Anything that makes our lives easier and helps get us out of any nasty situations, I'm a huge fan of. So this is a great step forward. On the Macs, the auto on probe heat position that I've just been speaking about, this is now standard. The engine anti-ice panel has got a new amber caption, which is engine anti-ice. So we're actually back to the stack of 3 captions that we had way back on the 1200 series. I mean, obviously they're different, but it's interesting to see it come full circle. So these engine anti-ice captions, these illuminate when the engine cowl anti-ice system has been inhibited due to a system failure, or when the engine core anti-ice valve fails closed. So it's telling you that there's a problem with the anti-ice and it's no longer being supplied. The other change is that these 4 lights along the bottom row, if you recall, they all used to be blue, and they all had the word open at the end of them. So it was left or right valve open, cowl valve open. So what Boeing have done is they've removed the word open and they've changed the logic and got rid of the blue, and now they will only illuminate if they're in transit, which is normal, or if the valve's in disagreement with the switch position. In other words, it's not working as intended. So if you were to switch wing anti-ice on and you weren't getting wing anti-ice, you would have one of or both of the valve lights in amber, and the same with the engine anti-ice. So again, for my money, this is an improvement. It's a bit more logical. And it's showing better functionality than the old blue light system, and it keeps things standard with the rest of the amber caution logic throughout the aircraft. So yeah, I'm a fan of these changes. All right, on to window heat. Windows 1 and 2, so the front and side window, and 4 and 5 if you've still got them installed, these are electrically heated. There is a customer option for window 3, that's the rear side window, to be heated as well. Now the window heat works by passing a current through a conductive coating in the laminate, and this is, you can't see it, so I'm not able to photograph it for you, but this conductive strip runs the full length of the top and bottom edges of the windows to send the current all the way through. A common misconception, if you ask some folk, is that these are where the window heat are introduced. that I've got in the photograph, they're not. They are the primary and spare temperature sensors that you see in this photograph. So they are just there to the resistance type temperature sensor, and these feed back into the window heat control units, which I'll show you in a second. You only need one of these. Only one of these it works at any one time. You've got a primary and a spare, and that really is just for ease of maintenance. That if the primary were to fail, you don't have to replace the whole window until the second one fails, because replacing the window is a big job, and it saves you getting stuck down route. So that's what these are. These are just temperature sensors to detect an overheat condition. They're not where the full window heat current is introduced. So about the window heat switches, if window heat is switched on but the on light is extinguished, then that could be because the heat controller has detected that the window is becoming overheated. Now this you often see when you're parked up on a turnaround on a hot destination, and the sun's beating in through the window, and if you happen to to look up and notice at this panel, you may see, and it's often the rear side, or the left or right side windows that this happens on. You'll notice that one of the green on lights is extinguished. This is not a problem if it's a hot place. Just touch the window, and if it feels hot, then that's probably what's happened. This window heat will be automatically restored when that window has cooled down. Now if you're concerned about it and you want to verify that window heat is still available, then you can do a power test. So move this spring-loaded switch in the middle down to the power test position, and the green on light will come back on. Don't hold it there, because you don't want the thing to go to a full overheat condition, but just momentarily blip it down, check that the green on light comes on, and then you've got the peace of mind that the system's still functioning normally. Note that the overheat protection is still available when you do the power test, but as I say, don't hold the switch down. Now if an overheat light illuminates, then that means that either a window is overheated or electrical power to the window has been interrupted. The affected window heat should be switched off. Give it anywhere between 2 and 5 minutes to cool down before switching it on again. So, I'll say that there's two stages of overheat. There's the not fully overheated, it's becoming warm, which will take power off, and you'll see the green on light extinguish. If it goes beyond that condition and it does fully overheat, then you'll get the amber overheat light. Okay, I said I'd mention the window heat control units. These are they, 4 of them, and they're in the E&E bay. I can't let one of these presentations go without showing you one of these, or a unit in an E&E bay. Well, this is today's. Obviously, you as pilots, or we as pilots, we'd never have need to see these units. It's all in the realm of the engineers, but personally as a pilot, I find it interesting to see these things and see what they're like, and see what's going on behind the scenes. So each window heat switch, 4 switches, has got its own control unit. 4 switches, 4 control units. These control the power to the windows. They monitor the window temperatures. They control the on or amber off and overheat indications. They've also got bite tests in them, which illuminate if there are faults either in the control units, the window sensors, or their power sources. So these are the brains and the computers behind each one of those little switches that you switch for window heat. Okay, on to engine anti-ice. It uses 5th augmented by 9th stage bleed air from the associated engine to heat the engine cowl to prevent ice buildup. The fan blades and the spinner are not heated. unlike the 1200 series where the spinner was heated and the stator vanes were, on the Classics, NG and the Max, they're not heated, which is how you can see photographs like this of ice formation on the spinner. And where the ice also forms, and this is a top tip for you when you're doing your walkarounds, you may not see the ice just because it's not on the spinner. Doesn't mean to say it's not behind the fan blades. The place where it forms first is behind the fan blades, so that might be easy to miss on a walk around. So if you think icing conditions are or have been present, maybe worth just putting your finger behind the blades just to detect if ice is there. It forms there because that's the pressure difference, between the face and the rear of those blades. That's why the ice forms there. Engine anti-ice, it's an anti-icing system, so it can be used continuously and should be used continuously in icing conditions. The amber cowl anti-ice lights will illuminate if there's an over temperature, 440 degrees C, or over pressure condition in either duct. In this situation, thrust on the associated engine should be reduced if conditions allow until the light extinguishes. Now, just a word about this phrase that you often see in the QRH, if conditions allow. When it's associated with thrust reduction, what Boeing really mean here is, well, there are two easy cases that you can imagine. The first is if train clearance is critical and you need the thrust to get over that, and the second case is if the other engine is malfunctioning in some way or has already been shut down. Then of course it's not a good idea to reduce thrust on your only remaining live engine. But obviously it's a judgment call by the captain on the day. So if conditions do allow, then reduce the thrust, and the cowl anti-ice light should extinguish. Okay, on to wing anti-ice. Unlike engine anti-ice, the wing anti-ice uses bleed air from the main pneumatic manifold. This is to ensure that you got a source of bleed air during engine out operations. Only the leading edge slats have got wing anti-ice, so not the leading edge flaps with the surfaces inboard of the engine. So it's only the surfaces outboard of the engine. And furthermore, on the NG and the Max, the outboard slat is not de-iced, as you can see from the photograph. And that, I believe, is due to the excessive bleed requirements that there would be if that extra slat was also de-iced. Now, I must admit, the first time I saw it, I was a bit horrified. I mean, of course, I'd done the differences course and read the manual, but it had, I must admit, passed me by that the outer slat was not de-iced until I saw it for real. Boeing have obviously assessed this and decided that the associated loss of lift on that outboard portion of the wing, I guess due to the taper of the wing, because the chord's so much narrower there, is not significant. The bulk of the lift of the wing comes from the inboard section. That's where the wing is thickest. That's where where the greater area is. Out at the tip, there's less lift. So I guess Boeing said it's okay. Surprising, but there we go. Use of wing anti-ice above flight level 350 may cause bleed trip-off and possible loss of cabin pressure, and that's a quote from the FCOM supplementary procedures. I guess just to extend this this argument a bit further, if the outboard slat had been de-iced or had a de-icing facility, then this flight level 350 limit might have been significantly lower. Well, it will have been. I mean, hypothetically, if it had come down to say 250, that might not be acceptable because you might still need to use wing anti-ice at those lower levels because you may not be out to the tops of the clouds yet. So I guess this is all in the mix for why the decision-making process was at Boeing for leaving that outboard slat de-iced, not de-iced. The wing anti-ice system. This is how it works. This is a photograph of the slats extended. What you can see on there are the sort of brownish coloured pipe in the middle. That's the telescopic duct where the air for the wing anti-ice comes in. So every slat has got a telescopic duct like that. So that's Teflon coated to allow so it doesn't stick and impede the extension and retraction of the slats. It then, when it reaches the leading edge, it turns 90 degrees left and right and runs through it goes into a feeder tube where nozzles blast out this hot air into the slat leading edge. It's then exhausted through these holes, which you can see highlighted there. That's where the hot air then comes out. The other things you can see here, I mean, I haven't marked them because I'll come back to this when I do the flight controls presentation, but below the telescopic duct, that's actually the actuator rod for the slats. And the other surfaces you see, there's one above and two down below. They are they're just the slat tracks. They keep the slat in position. Anyway, I digress. So wing anti-ice, it's extremely effective. It usually shifts any ice within, I don't know, 10-20 seconds. So it's normally used as a de-icing system in flight. So you don't have it on all the time. Like you would engine anti-ice. Put it in applications of around about a minute or until the ice is gone. On the ground, it should be used continuously in icing conditions. And a random fact for you that Boeing released: according to Boeing, the NG wing thermal anti-ice system can blow hot air on the wing leading edge, equivalent to about 6 full-size, that's 100,000 BTU household furnaces. There you go. Who knew? So it's a heck of a lot of hot air. The logic for the switches in the operation is that on the ground, the wing anti-ice valve, this is not the switch, will cut off if either thrust lever is above the takeoff warning position. So that's 32 degrees on the classics or 60 on the NGs, or if an over temperature condition is detected. But it'll be restored after the thrust is reduced or the temperature drops, and it's done this way to allow you to perform engine run-ups without having to check that the wing anti-ice is still on afterwards, which, you know, is again great news for us. It's another pilot saver there. The switch, though, because what I was just talking about there was the valve, but the switch is solenoid held, and that'll trip off at liftoff. This is for performance considerations because, as we've already discussed, the bleed air penalty for wing anti-ice is considerable. On early systems, so this is on the lower photograph, those with the ground test position like was fitted on the originals and some classics, the wing anti-ice switch on the ground, wing anti-ice is inhibited until liftoff. So it's armed, and this is opposite to the present system, so a little bit confusing there. Fortunately, that's gone, and we've just got the nice, straightforward, very logical two-position switches that we've got now. On the Max, as I've already said, the wing and engine valve open lights use until the Max, we've always used the bright blue, dim blue logic for the valve position being in agreement or disagreement. The wing left and right valve open lights, they might remain bright blue after an engine start or during taxi, and that's because they're pneumatically operated valves. Remember, electrically controlled, pneumatically operated. So if you've got one or both stuck in the bright blue position, then you can get them to open with a modest amount of engine thrust. So just a little zizz on the thrust levers, and the valve should go back to dim blue. The anti-ice has an effect on speed and certain limits. So whenever wing anti-ice is used, the SMID, so obviously this is only on the NG and the Max, it applies a thermal anti-ice bias. So this increases the stick shaker and the minimum manoeuvre speed bars by enough to account for 3 inches of rough ice on the leading edge devices. Now, what exactly that amount is in knots depends on a whole load of things, the specific variant of the aircraft and the various other factors. So that's why we can't say how many knots it puts on. All we need to know as the pilot is that it puts on enough to account for 3 inches of rough ice, which is a heck of a lot. You'll also be able to observe that the M1 limits reduce slightly on both the M1 indicators and the FMC M1 limit pages, and that happens on all series of 737s. When the engine or wing anti-ice is switched off again, the indications return to normal, so back to where they were before, unless wing anti-ice was used for more than 5 seconds, in which case the TI bias latch will be set for the remainder of the flight. Ice detection now. There is an ice detection system available as an option on classics, NGs, and even the Max. Aircraft with this option have got an extra probe on the lower left fuselage, which is the ice detection probe. Now that works by, it has a magnetically induced vibrator inside it, and if ice starts to form on the vibrator, the frequency of the vibration will change, and an icing signal is then sent to the flight deck. If ice is detected on the probe, a heater is turned on to melt the ice so the probe still continues to function. If no ice is detected for 60 seconds, then a no ice signal is sent up to the flight deck. And in the flight deck, what we see are the 2 lights up there, icing and no ice. So when the probe senses an ice build-up, the icing light illuminates. When ice has previously been detected but the probe is no longer detecting ice, the icing light will extinguish and the no ice light will illuminate. It's a bit annoying flying these sometimes because they need to be pushed to cancel each time. I get it with the icing light, but the no ice light, really, do we need to push to cancel that? Anyway, that was the logic, and that's what we have. I guess it's better than nothing. There's also an ice detector amber light on the anti-ice panel, which will illuminate when the ice detection system fails. Before the days of the ice detection system, we on operators that had it, we just had this band, this matte black band on the leading edge. It's entirely at the operator's discretion whether these are fitted. What I've found is that airlines that operate in northern climes have these. So Norwegian have got these, and I think Maersk had them, probably SAS did as well. So they're operators which are used to operating in more conditions of icing, and I guess they found them useful. I find it's very much up to the individual crew whether you find them useful or not. They don't always work, but I guess they're better than nothing. Now these are normally applied at the outermost point of the de-ice sections of the slats, where they can be most easily seen by crew. So there's no point in putting them on the outboard slat because that isn't de-iced. But you want them on the most outboard position of where the de-icing is, so that you can easily see it from the flight deck windows. I mean, on the 8 and 900 series, and even more so, I guess, on the Max 10, it's difficult to see too much of the wing because it's that bit further back. Okay, so on to airframe visual icing clues. Um, it's up to the crew to spot ice formation and take the necessary action. So what I've done over the next few slides, I've put in a couple of photos of some places where ice accretion is visible from the flight deck, just to help your decision making process as to what kind of ice you've got. Again, I emphasise that engine anti-ice should be used whenever the temperature and visible moisture criteria are met, and not left until ice is seen to avoid in that ice buildup which may shed into the engine. I stress this point because guys coming from other aircraft types may have used engine anti-ice in a different way, but certainly on the 737 we use it all the time. The ice criteria are met. Okay, so ice under the windscreen wiper blades, it's one of the first places that ice will form. What actually happens is that rain will, if it's falling, or indeed moisture from clouds will impact the windscreen there below the wiper. It will melt because of the window heat, if it was falling of ice, and it will run up to the bottom of the wiper and get caught in the corner there, in that stagnation point. The pressure is low in there. It's different to the rest of the windscreen because of that stagnation point, and ice can form there where it would not normally form on the rest of the aircraft because the pressure is different there. So that, to me, it's a first sign of icing, but it's not actually indicative of ice accretion on the rest of the airframe. That, to me, is light icing. Now, when you get icing forming on the wiper nut, there is no stagnation point there, and if icing is forming there, it will also be forming on the rest of the airframe. The weight and aerodynamic effect of ice forming on the not only just the wiper nut, because that's obviously insignificant, but on the rest of the airframe is significant, and this is why you've got a residual ice penalty of several tons on the landing field length limit graphs in the flight planning and performance manual. And as an example, for those of you that haven't got a copy of this manual, for a 26k 737-800 with winglets, on the auto speed brake graph, so this is the normal one we'd use, it states decrease weight by 6,800 kilos if icing conditions are forecast during any part of the flight. So obviously, whilst that's a dispatch thing because it's talking about forecast, it still goes that Boeing consider that the effect of airframe icing to be so significant that it gives you a nigh on 7-ton penalty for landing field length. So it is significant. So to summarise, if you see ice build up on the wiper nut, then that to me is moderate icing. Now, these photographs, the top one was in a Classic, as I recall, the bottom one was in an NG. For ice to form on a flat, heated windscreen, conditions must be pretty bad. On the lower photo, you can actually see the shape of the airflow lines in the ice formation there. So that, I mean, from memory, we were going fairly quickly. I think that was climbing up through the top of clouds. So we must have been doing 280, 300 knots, and yet ice was still forming. Volume 1 supplementary procedures states avoid prolonged operation in moderate to severe icing conditions. Now, obviously, sometimes it's unavoidable, and in this case, it was. We were climbing through, as I say, cloud-bearing or rain-bearing cloud, frontal cloud, and that ice formed very, very quickly. It went from nothing to as you see in that photograph, in under a minute. That to me is severe icing, and those are the conditions that the Vol 1 is telling you to avoid prolonged operation in. Okay, the other form of icing we get is what they call non-environmental icing. There's actually none shown on this photograph. You normally see it on the ground on a turnaround, but I actually, would you believe, in all my library of thousands of photographs, I didn't have one of it, not on the upper surface of the wing anyway. So what I'm showing you here is just the markings for those of you who are not familiar with them in that red area. So the NGs have got a problem with frost forming after landing on the wing above the fuel tanks where the fuel is being cold soaked. It's officially known as wing upper surface non-environmental icing, or cold soaked fuel frost. The reason for the formation of this is the increased surface area of the fuel that comes into contact with the upper surface of the wing. And this is because the fuel tanks on the NG were moved outboard to accommodate the longer landing gear that was required for the increased fuselage lengths of the NG family to reduce the risk of tail strikes. So it all comes back to the fact that on the NG they were anticipating an 800 and a 900 series. And for those of us that flew the 400, you recall how tight the tail strike risk was on the 400. So that Boeing overcame that by increasing the length of the landing gear, and as I say, the domino effect of that, the kind of butterfly's wing effect, was this cold soaked fuel frost. When this was discovered, the only solution with this, because before cold soaked fuel frost was permissible, it was the clean wing concept. The only solution used to be that you had to limit your arrival fuel to less than about 4 tons, or get a full de-icing every time. Anyway, fortunately Boeing issued guidance on the acceptable location and amount of upper wing frost. An aircraft delivered after July 2004 have had the wings marked with the permissible area for cold soaked fuel frost, and of course other aircraft can have it retrofitted, the markings applied, and the markings are those given in the red area there. The photograph I do have is underneath, which is arguably just as useful. Now, the Boeing advice for what frost is permissible underneath is as follows. Flight crews should visually inspect the lower wing surface. If there is frost or ice on the lower surface outboard of measuring stick 4, there may also be frost or ice on the upper surface. The distance the frost extends outboard of measuring stick 4 can be used as an indication of the extent of frost on the upper surface. Well, that's great if you know where measuring stick 4 is, and that's part of the reason why I've put it here. So the measuring sticks are those small red circles that you see in the inspection panels, and I've shown measuring stick 3 on the photograph. Measuring stick 4 is 3 inspection panels away from that, so I've sort of photoshopped it on up there as the location of measuring stick 4. So if there's any frost out there at measuring stick 4, then you probably need to get de-iced. Now, it should be noted that if the thickness of frost on the lower surface is greater than 1/8 of an inch or 3 mil, then a physical inspection of the upper surface frost is required. Well, we don't go around with a ruler to measure exactly what 3 mil is. You can, if you can reach, you can try scraping it with your thumbnail and estimate it. But for me, a useful sort of guideline would be, if you can see markings or decals behind something, then you've got less than 3 millimeters. So it's probably more applicable on the other wing, on the upper wing, where you've got markings. But if the markings are obscured by the frost, then it's probably more than 3 millimeters. Again, these are just my own guidelines. That this is not official Boeing advice. You as the crew on the day have got to make your own decisions. But that they're the criteria I use, and you may find that helpful to assist your decision-making process. Now, other non-environmental icing, this is the common one. So sometimes frost can be seen along distinct lines along the vertical stabilizer. It's another form of non-environmental frost, but this actually forms where the skin is touching the spars inside the fin, that which have become cold soaked on a long flight. Now, my view on this is that as the fin is a non-lifting surface, this frost is acceptable. If you think what the fin is for, it's for directional stability, and that, to me, the directional stability is not affected by this frost. It's that frost is also, I would suggest, probably not having any significant effect on the operation of the rudder either. And I think for anybody that says it is, you've only got to look to the if you're worried about the effect this frost might have on the rudder, which for me would be the only argument for why this should be removed, then cast your mind back to the effect of ice on the outboard slat and the effect of that on the aileron. Now, if Boeing considered that the outboard slat could not be de-iced and that the aileron function was unaffected, then I would suggest that the operation of the rudder would be unaffected by this frost here. Again, this is only my opinion. You as the crew on the day, I can't stress this enough, you've got to make your own decisions and your own calls, or follow your company advice in case it's different to what I'm saying here. Okay, onto the windscreen wipers. I would say that on the early generations of the 737, the windscreen wipers were one of the aircraft's worst design features. They're so noisy that they're probably more of a distraction than a benefit. And it always seemed like if you ever attempted to use them on high mode, that they felt like they were about to fly off. Awful things. But there we go. That's all we had. One of the most welcome new features of the NG and also on the MAX is the vast improvement to the windscreen wipers. They can be independently controlled. They've got an intermittent position like the originals had. If you look at the photo top left there, you'll see they had a low 1/2 and 3/4 position, which was done away with on the classics, but came back on the NG. But the best thing of all about the wipers on the NG is that compared to the originals, they're almost silent, so you can use them without distraction. Note that on the NG and the MAX, there is no rain repellent, which is there on the originals and the classics, and that's the reason for the gap above the right-hand wiper control on the NG. So, talking about rain repellent, this is what it looked like, and if you've not been on the 737 for a decade or two, then you'll have probably never seen this. Rain repellent was something that you squirted onto the windscreens to stop the rain being on there. It was a hydrophobic liquid. It was removed due to worries about the environment and the health effects of the fluid. It was called Rainbow, and it was a low toxicity solvent, but unfortunately it contained freon 113, which is a CFC. The canisters which held it were stored behind the captain's seat, as you can probably just make out the J track there on the photo. They had been known to leak, particularly after a change of canister. And as I say, it was low toxicity, but it was enough of a concern that the pilots and the pilot unions, sort of pressed Boeing to do something about it. In 1991, Boeing added a substance called D-laminine, which had a strong smell of orange peel, so that if it leaked, if you smelt oranges in the flight deck, then you'd after landing you get out and tell an engineer and have it cleaned up, so that you didn't have to inhale the fumes. The rain repellent buttons, which were, as you've already seen above, the wiper controls were removed after the classics, and windscreens are now treated with a hydrophobic coating to repel rain. So rather than the hydrophobic liquid, which was the Rainbow, there was actually a proper semi-permanent coating put on the windscreens, which did the job of this. One final word about the rain repellent. The graphic up there in the top right, the newspaper cutting, that was a sad end to a 737-200 in May '92. This one was written off by a heavy landing in a rainstorm, and the report stated that the pilot's misuse of rain repellent caused an optical illusion. I haven't actually seen firsthand the report, but they're the extracts which are often quoted. Anyway, rain repellent is a thing of the past. Since early 1994, all Boeing aircraft, so not just the 737s, they've been built with a surface seal coated glass from PPG Industries, which has a hydrophobic coating. The coating does deteriorate with time depending on wiper use. So again, top tip to us all out there: if you use wipers on dry windscreens, apart from the fact it will be noisy and ineffective, you'll actually be removing the hydrophobic coating from the windscreen. You could also scratch the windscreen as well. So really try not to use the wipers when there's very little rain on the windscreen. The hydrophobic coating can be reapplied if you find that it's a problem to you when you're flying. The windscreen doesn't look like it, the hydrophobic coating's there, then put it in the tech log and the engineers can reapply it. It's not a quick job, but same with all sort of defects. If you as crew put it in the tech log enough times, then eventually it will get done. So that's it for me on ice and rain. If you enjoyed the video, please give it a like, subscribe to my channel, tell your colleagues, spread the word, and if there's enough interest, I'll continue doing these videos for everybody. Thank you.